Welcome to the NPTEL course on computer system optimization for machine learning. This is the 6th lecture of this course. We will briefly go over the recap of from the last course or the last lecture. Then we will discuss a quantitative example of flattening. After that, we will discuss something called fully connected layers. Okay. So in the last lecture, we talked about flattening. So if you remember, the major reason we wanted to do flattening, because if we naively implement the convolutional operation, then we have a 7-layer nested for loop, which is cumbersome, which is difficult to write and all those things, right. If we perform flattening, then we can represent the convolutional operation into matrix multiplication, right. So in the last lecture we saw that what if we have multiple channels, multiple filters, then how can we do the flattening. So this is just quick recap. If we have different channels of the filter, then we have to stack the filters in the same row, or if we have to append the filters, different channels of the filter in the same row. If we have once we have multiple filters, then we have to stack the filters on top of each other, right, I mean in different row, right. Similarly, this particular matrix was obtained, or this particular matrix is the flattened version of the input feature map, and then since we have two channels in the input feature map, that is why we have stacked the different channels of the input feature map into different rows. Okay. So if we do this matrix multiplication, then we will get the different channels of the output feature map. So remember, yes, flattening is good. With flattening, we are just performing matrix multiplication. We are no longer doing that 7-layer naive for loop. But then remember, we have to do some pre-processing, right? We have to make this flattened version of the filter. We have to make this flattened version of the input feature map. That's one thing. And then we also need to do the post processing. So remember, this is the output feature map, right. From this output feature map, we get two channels where we have all the pixels, right. So this is how we represent the output feature map when it goes to the next layer, correct. So this is the post processing, correct. So there will be some time consumed by the pre-processing step as well as the post processing step. Now depending on the number of channels or different parameters of the deep neural network or this convolutional neural network, it might happen that the pre-processing and post-processing takes so much of time, it actually masks the advantage of flattening. It might happen, right. You can actually do implement this in C or C++ and then see whether we have benefit all the time or not. So that is what we discussed in the last class. Now let us see one quantitative example of this flattening. Okay. Now in this example, the numbers whichever I am showing is actual numbers, they are no longer the indices. So let us say we have a single channel 4x4 image where these are the pixel values 1, 2, 3, 4, 5, 6, 7, 8. I mean, yeah, you can argue that these are the indices, but apart from indices, let us say those are the pixel values also. Now our job is to perform a convolution operation where this image is convolved with a filter, where the kernel size is 2x2, no zero padding, stride length of 1, no bias, only one output channel, and let us say this is the weight, or these are the weight values, right. Now what will happen? So during the convolution operation, first these weight values will get multiplied with the first image patch, which is nothing but this particular patch, right. And then since stride length is 1, it will slide. The filter or the weights will slide. So it will slide onto the second image patch, this 2, 3, 6, 7, and then it will go to the next image patch 3, 4, 7, 8, and then the row of the first row is exhausted, right. All the columns are exhausted, correct. So then it will go to the next row. So this is the, since stride length is 1, when it will slide row wise, it will again slide, it will go to the next row, okay, because the stride length is 1. So this 5, 6, 9, 10 is the image patch 4, this is image patch 5, and so on and so forth. So basically with this each of these image patch, this weight will get multiplied. I mean, again, when we say multiplied, we will perform the element wise multiplication and then add all the values to obtain one pixel of the output feature map, right. Now remember, when we convert the filter trace into matrix, this 1 2 5 6 will go to one column. So, that is how we flatten the input feature map. This second patch will go to the second column, third patch will go to the third column, and so on and so forth. So, that if we multiply this flattened input feature map, then this flattened input feature map with the flattened version of the filter, then we will get the flattened version of the output feature map. How does it happen? So, the matrix of weights for the convolutional layer can be flattened into a vector, we already saw in the last class. So, this was the flattened version of the convolutional, or the flattened version of the filter weights, right. So, that is why this 1 2 3 4 is getting multiplied, and this is just a vector matrix multiplication. Remember, we already assumed for this example we just have one channel of the input. So, I mean, of course, if there is one channel in the input, we have only one channel in the filter also. We also assume that there is only one filter. Okay. Now, this 1 2 3 4 will get multiplied with this flattened version of the input feature map to get all these values. Okay. So, you can verify yourself this 1 2 3 4, if they get multiplied and then all the product get added, then we will have these values, and so on and so forth. So, that is how we can perform this flattened convolutional or flattened matrix multiplication to mimic or to get the same output as convolutional operation, right. Now, so that is all about convolutional layer or the convolutional operation. So, remember, when I was showing you the full picture of a convolutional neural network, the first few layers or all the initial layers or most of the layers are convolutional layers, right. But then there were 2 or 3 fully connected layers also, right. So, now let us see how these fully connected layers operate. So, the fully connected layers are, I mean, they are not too different from the convolutional layers. The only difference is the filter size is exactly same as the input feature map size. So, here you see that the input feature map size is h by w. For fully connected layer, the filter size is also h by w, right. Now, imagine you have a 3 by 3 image, or let us say 5 by 5 image. Let us assume that there is only one channel of that 5 by 5 image. Now, if you have 5 by 5 filter, you will just overlap once and then get one output, correct. There is no way you can stride in the left, or I mean stride in the right or in the downside, right. So, that is the fully connected layer. So, if we have fully connected layer, then the output size will be just 1 by 1. So, that is why you can see this is just 1 pixel. Okay, although I mean you can see a square, but this is the size will be 1 by 1, because the number of filters and the size of the filter and the size of the input feature map is exactly the same. I mean you can do it mathematically also, right. If you have size of the input feature map as h, or let us say height of input feature map is h, and the height of the filter is r, then and the stride length is 1, then this was the formula for to get the height of output feature map. Now, here r equals to h, so you will get the height of the output feature map as 1, right. So, that is why you can see that there is only 1 pixel in the output feature map. Since we have m filters, we have m number of channels in the output feature map. So, remember, we had C channels, but then all those C values which we get from the convolution of h by w filter with h by w image, you will get one value for each channel, and then all those values will get added to produce one number, which is nothing but this 1 by 1 value. Now, since we have m number of filters here, we have total m number of channels in the output feature map, right, and this is the this is how fully connected layers operate. So, this is same as convolution, but since we have the size of the filter exactly same as the input feature map, the pixel or the size of each channel of the output feature map is just 1 by 1, that is all, right. Now, again, if we have n input feature maps, so you will have n number of output feature map, correct. So, that is how these fully connected layers operate. Now, let us see when we do the flattening, then how this fully connected layer look like. So, flattening will work in same way. So, remember the only difference is here the number of column is the number of column in the flattened input feature map is just 1, because we will just have one column in the output feature map, right. Now, we flatten this 3 dimension into 1. This C is the number of channels in the input feature map, and H and W are the height and width of the filter. So, if you remember, I mean for the regular convolutional operation also we just flattened into CHW by M dimension of the filter, right. So, all filters of for the input feature maps are flattened into one row of CHW. Now, we have M such rows, right. Remember, we have M filters. If we have multiple filters, then each of the flattened filter will go into one row, right. So, we have M such rows. There is a typo here. So, we have M such rows for each of the each for an output channel, right. So, if we like multiply this M these two matrix M by CHW, this gets multiplied by CHW by 1. So, you will get a M by 1 matrix, right, which is nothing but the output feature map, right. Now, to perform the matrix multiplication, input feature maps also need to be flattened into CHW rows. After the multiplication, the output contains one point, like see this is 1 means this is just one pixel. So, each of the pixel for each these are the pixel for each of the channel in the output feature map. So, after multiplication, the output contains one point or one pixel for each for all M output channels, right. So, that is how this flattened fully connected layer operate. Now, let us just see that how we actually get the multiplied output. So, first from this CHW, this again this CHW is nothing but one particular filter, right. So, this vector row vector will get multiplied with this input feature map to get one value, to obtain one value. Now, this one value is coming from one filter, right. So, since there are M such filter, we will get M such values, and that M is nothing but the number of channels in the output feature map, right. Now, once the first row is done, we will move to the second row to get the second pixel from the second filter, second pixel of output feature map from the second filter, and so on and so forth, right. Now, if we have n number of inputs, so remember as I was saying that whenever we perform this inference, we might not have just one input, rather we might have n different inputs, right. So, if we have n input, then we have to have n output. So, each of the output will be of size m by 1, right, because why m by 1? Because we have m number of filters, and then each filter is contributing to just one pixel in the output feature map, right. So, that is why we can stack the input feature map for different input in different column to get the output feature map, which is corresponding to different input feature map will again be stacked in different column, right. So, after flattening, having a batch size of n turns the matrix vector operation into a matrix multiplication. So, if we had batch size of 1, let me go to the previous slide. If we had the batch size of 1, it was just a matrix vector multiplication. Now, since in this case we have a matrix, we have a batch size of n, we are having this matrix operation or matrix multiplication, right. So, that is the flattened fully connected layer. Now, again I mean you might already imagine. So, once we have this CHW for one specific filter, that will get multiplied with this CHW for one particular input image to get one pixel in the output feature map for one of the channels, right. Since we have M filters, we will have total M channels, correct. Now, the same CHW will get multiplied with the next input feature map to obtain the same the next pixel of the same channel, and so on and so forth. So, once all the input feature maps are obtained for one particular channel, then we will go to the next filter to which contributes to the next channel of the output feature map, right. So again this will also be like going, so it will be not sliding, I mean it will, the multiplication will happen step by step, right. Again the same flattened filter is getting multiplied by the input feature map to obtain the corresponding output feature map. Now one important aspect is, if we think like how much temporal locality. So temporal locality is nothing but reuse of data within a time frame is happening for this implementation. None. We are not reusing anything, correct. So we are just taking bunch of values, one row vector that is getting multiplied by one column vector to obtain one pixel. But then remember, some of the values in this row vector or some of the values in the column vector, or not in one column vector, but with respect to different column vector or with respect to different row vector, some of the values are here, some of the values between these two rows, some of the values in, let us say, between these two columns are same, right. But still we are not reusing. Now if some of these values are same, then some of the matrix multiplications are not some of the matrix multiplication, but some of the element wise multiplications are actually getting repeated, right. So that you can imagine, I mean in convolutional operation itself, some of the element wise multiplication will get repeated because the same filter is getting projected on the entire image, right. So some multiplication can be repeated, or some access to the filter or some access to the input feature map can get repeated. But here when we perform this flattening, we are not using any temporal locality, there is no reuse of data within a frame. Okay. So this is just for your information right now, later we will see how does this affect. So yeah, I mean that's all for this lecture. This lecture was rather short because I wanted to show you one example, and in the next lecture we will see some of the nonlinear operation, and then we will see some of the real convolutional neural network. Thank you.